Hi students, in today's session we are going to discuss about the models of nuclear structure. The precise nature of the forces acting inside the nucleus is not known. We had already stated that it is much easier to study about the atomic structure and to determine the atomic composition than to study about the nuclear structure, because to disintegrate an atom only a few electron volts of energy is required, whereas to disintegrate the nucleus, a very large amount of energy in the order of 100 MeVs is needed. So, it is very difficult to disintegrate the nucleus and study the nuclear structure. Hence, what we do is we resort to the use of uh, nuclear models. We resort to the use of certain models in order to predict the properties of the nucleus. Now, how do you choose these models? These models are chosen based on some extrinsic similarity in the properties between the model chosen and the nucleus. And this analogy between the properties of the atomic nuclei and the model chosen helps us in predicting the properties of the nucleus. അതായത് ഒരു ന്യൂക്ലിയസിന്റെ സ്ട്രക്ചറിനെ കുറിച്ച് പഠിക്കാൻ വളരെ പ്രയാസമാണ്. ന്യൂക്ലിയസിന്റെ ഉള്ളിൽ ആക്ട് ചെയ്യുന്ന ഫോഴ്സസിന്റെ കൃത്യമായ നേച്ചർ മനസ്സിലാക്കാനും വളരെ ബുദ്ധിമുട്ടാണ്. ഇതിനൊരു കാരണം ന്യൂക്ലിയസിനെ ഡിസിൻറ്റിഗ്രേറ്റ് ചെയ്യാൻ വളരെ വലിയ എമൗണ്ട് ഓഫ് എനർജി ആവശ്യമാണ്. അപ്പോൾ ഡിസിൻറ്റിഗ്രേറ്റ് ചെയ്ത ന്യൂക്ലിയർ സ്ട്രക്ചർ പഠിക്കുക എന്നത് വളരെ പ്രയാസകരമായ ഒരു കാര്യമാണ്. അപ്പോൾ ഇതിനെ മറികടക്കാൻ എന്ത് ചെയ്യുന്നു വെച്ചാൽ ന്യൂക്ലിയർ സ്ട്രക്ചറും അതിൻ്റെ പ്രോപ്പർട്ടീസും ഫോഴ്സിൻ്റെ നേച്ചറും എല്ലാം പ്രെഡിക്റ്റ് ചെയ്യാനും അതിനെ കുറിച്ച് പഠനം നടത്താനുമായി വി മേക്ക് യൂസ് ഓഫ് ന്യൂക്ലിയർ മോഡൽസ്. ചില മോഡലുകളെ നമ്മൾ യൂസ് ചെയ്യുന്നു. എന്നിട്ട് ഈ മോഡലും ന്യൂക്ലിയസും തമ്മിൽ കുറേ സിമിലാരിറ്റീസ് ഉണ്ട്. അത് വെച്ച് ഈ മോഡൽ ഉപയോഗിച്ചുകൊണ്ട് നമ്മൾ ന്യൂക്ലിയസിൻ്റെ സ്ട്രക്ചറും അതിൽ ആക്ട് ചെയ്യുന്ന ഫോഴ്സസിനെ കുറിച്ചും അങ്ങനെ ന്യൂക്ലിയസിൻ്റെ പ്രിസൈസ് നേച്ചറിനെ കുറിച്ചും നമ്മൾ പഠനം നടത്തുന്നു. So one such model is the liquid drop model, where we say that the nucleus and the liquid drop are similar in many ways extrinsically. അതായത് ആദ്യത്തെ മോഡൽ to study the precise nature of nuclear forces is the liquid drop model. അതിൽ നമ്മളൊരു ലിക്വിഡ് ഡ്രോപ്പിനെയാണ് ഇവിടെ മോഡലായി കണക്കാക്കുന്നത്. ആൻഡ് ദി എക്സ്ട്രിൻസിക് analogy or similarity in the properties of the liquid drop and the nucleus is considered, and based on that we study about the nucleus. Another model is the shell model, where the similarity or the analogy between the properties of the atomic nuclei and the electronic shells of an atom is used in the shell model. Now let us begin the liquid drop model. Here, the forces acting inside the nucleus is considered to be similar to the molecular forces acting in the droplet of a liquid. This model was proposed by Niels Bohr. Now let us consider what are the similarities between the nucleus and liquid drop, so that we take the liquid drop to be the model in order to study about the nucleus. So it is because of the similarity existing between some extrinsic similarity existing between the nucleus and liquid drop, that we choose the liquid drop as the model to study about the nucleus. യഥാർത്ഥ ന്യൂക്ലിയസിനെ ഉപയോഗിച്ചുകൊണ്ട് ന്യൂക്ലിയർ പ്രോപ്പർട്ടീസ് അല്ലെങ്കിൽ ന്യൂക്ലിയർ സ്ട്രക്ചർ അല്ലെങ്കിൽ ന്യൂക്ലിയർ ഫോഴ്സസിനെ കുറിച്ച് പഠിക്കാൻ പ്രയാസമായതിനാൽ ന്യൂക്ലിയസിനോട് ചില പ്രോപ്പർട്ടികളിൽ സിമിലറായി നിൽക്കുന്ന മറ്റൊരു വസ്തുവിനെ നമ്മളൊരു മോഡലായി ചൂസ് ചെയ്തുകൊണ്ട് ന്യൂക്ലിയസിന്റെ പ്രോപ്പർട്ടീസ്, ന്യൂക്ലിയസിലെ ഫോഴ്സസ് എന്നിവയെ കുറിച്ച് പഠിക്കുന്നു. So let us see what are the similarities between the nucleus and the liquid drop. So the nucleus is supposed to be spherical in its stable state, just like the liquid which is spherical, just like a liquid drop which is spherical due to surface tension forces. So both are considered to be spherical in their stable states. Now, a force of surface tension acts on the surface of the liquid drop. Similarly, there is a potential barrier acting on the surface of the nucleus. അപ്പോൾ ലിക്വിഡ് ഡ്രോപ്പിന്റെ മുകളിൽ ഒരു സർഫസ് ടെൻഷൻ ഫോഴ്സ് ആക്ട് ചെയ്യുന്നത് പോലെ, സർഫസ് ടെൻഷൻ ആക്ട് ചെയ്യുന്നത് പോലെ ന്യൂക്ലിയസിന്റെ സർഫസിൽ ദർ ഇസ് എ പൊട്ടൻഷ്യൽ ബാരിയർ ആക്ടിങ് ഓൺ ദി സർഫസ് ഓഫ് ദി ന്യൂക്ലിയസ്. Now, the intermolecular forces in a liquid drop are short range forces. So the molecules of the liquid drop interact only with its nearest neighbors. Similarly, nuclear forces are also short range forces, and the nucleus interacts only with their nearest neighbors, leading to saturation at a constant binding energy per nucleon. So intermolecular forces in the liquid drop as well as the nuclear forces are short range forces. So that is also another similarity. Now this is the basic assumption of the liquid drop model. This point, that is, the intermolecular forces in a liquid are short range, and in a nucleus the nucleons interact only with their nearest neighbors, leading to the property of saturation. So this comparison forms the basic assumption of the liquid drop model. Next similarity is that on raising the temperature, the molecules evaporate from the surface of a liquid. Similarly, when bombarded with a nuclear projectile, that is, when you are providing with energy, the nucleus becomes a compound nucleus and gives out nuclear radiation. അതായത് എനർജി കൊടുക്കുമ്പോൾ, ടെമ്പറേച്ചർ കൂട്ടുമ്പോൾ ഒരു ലിക്വിഡ് ഡ്രോപ്പിന്റെ സർഫസിൽ നിന്ന് മോളിക്യൂൾസ് പുറത്തേക്ക് ഇവാപ്പറേറ്റ് ചെയ്ത് പോകുന്നു. അതേപോലെ നമ്മൾ ഒരു ന്യൂക്ലിയസിനെ ഒരു ന്യൂക്ലിയർ പ്രൊജക്ടൈൽ ഉപയോഗിച്ച് ബോംബാർഡ് ചെയ്ത് എനർജി കൊടുത്താൽ അതാദ്യം ഒരു കോമ്പൗണ്ട് ന്യൂക്ലിയസ് ആയി മാറി അതിൽ നിന്ന് അത് പിന്നെ സ്റ്റേബിൾ ആവാൻ വേണ്ടി ന്യൂക്ലിയർ റേഡിയേഷൻസ് പുറത്തുവിടുന്നു. So they appear similar. Next, when a liquid drop oscillates, it breaks into two smaller drops of equal size. Similarly, during nuclear fission, the nucleus breaks into two smaller nuclei. So all these are the similarities between or extrinsic analogies between a liquid drop and a nucleus. So we say that liquid drop can be used as a model to study about the nucleus, and we can go into the further studies based on this liquid drop model. Now here we are giving the semi-empirical nuclear binding energy formula for the nucleus. That is, using the liquid drop model, Weizsäcker proposed a semi-empirical formula for the binding energy of the nucleus, of a nucleus having mass number A containing Z protons and Z neutrons. അതായത് ഈ മോഡൽ ഉപയോഗിച്ച് ന്യൂക്ലിയസിന്റെ എന്ത് കാര്യമാണ് കാൽക്കുലേറ്റ് ചെയ്യപ്പെട്ടത്. അപ്പോൾ യൂസിങ് ദ ലിക്വിഡ് ഡ്രോപ്പ് മോഡൽ, വെയ്സാക്കർ എന്ന ഫിസിസിസ്റ്റ്, he proposed a semi-empirical formula. It's not an exact formula. It's a semi-empirical formula for the binding energy of the nucleus. Now, of any nucleus having mass number A containing Z protons and capital N neutrons. ഇത്തരമൊരു ന്യൂക്ലിയസിന്റെ ബൈൻഡിങ് എനർജി എത്രയായിരിക്കും എന്ന് കാൽക്കുലേറ്റ് ചെയ്യാൻ വെയ്സാക്കർ ഈ ലിക്വിഡ് ഡ്രോപ്പ് മോഡൽ ഉപയോഗിച്ചു. And the semi-empirical formula is given in this manner. EB, that is binding energy, is equal to A1 into capital A minus A2 into capital A raised to 2 by 3 minus A3 z into z minus 1 by A raised to 1 by 3 minus A4 into A minus 2z whole square by A plus or minus comma 0 A5 by capital A raised to 3 by 4. Here A1, A2, A3, A4, A5 are constants. Capital A stands for the mass number, Z stands for the number of protons, and N stands for the number of neutrons. Now let us discuss the first term in this equation. How does it contribute to the binding energy of the nucleus? So the first term is called the volume energy term, EV. Here, let us consider the bond energy between two nucleons in the nucleus is U. That is, let U be the energy between the two nucleons in a nucleus. So, energy of one nucleon is U by 2. Okay, this energy is shared by the two nucleons, so that energy of one nucleon is U by 2. Now, each interior nucleon is surrounded by 12 nearest neighbors. And we know that each nucleon interacts only with its nearest neighbors. That was one of our assumptions. Okay, just like a liquid drop. So you have to consider only the interaction of a nucleon with its 12 nearest neighbors. So the energy of an interior nucleon is, that is, the energy of one nucleon, we calculated it to be U by 2. Now we have a single nucleon surrounded by 12 nearest neighbors. So between one nucleon and its nearest neighbor, the energy is U. There are 12 such neighbors, so the total energy is 12U, so that the energy of one interior nucleon is half of it. That is 12 into U by 2, that is 6U. So this is the energy of one nucleon. There are 12 such pairs, that is the single nucleon forms a bond which with 12 such other neighboring nucleons. So the energy of one interior nucleon is 12 into U by 2, which is 6U. Okay. If all the A nucleons, A stands for mass number. Mass number stands for the total number of nucleons in the nucleus. And I am assuming that let all the nucleons lie in the interior of the nucleus. There are no surface nucleons. All are in the interior somehow. Then the total energy is given by 6U. 6U is the energy of a single nucleon into capital A. This is the total number of nucleons. So the total volume energy is given by 6 AU. Here 6 is a constant, U is a constant for a given pair of nucleons. So I write it as EV, that is volume energy, is equal to A1A. That is, volume energy is directly proportional to A, and it leads to an increase in the binding energy. That is, as the number of interior nucleons increases, it becomes more difficult to remove one nucleon from the nucleus, or the volume energy term increases or adds to the binding energy. So it is given as a positive value. The volume energy term adds to the binding energy, so it is given as a positive term. Okay, next we come to the second term. So the second term is the surface energy term, ES. So there are some nucleons. In the volume energy term, we consider all the nucleons to lie in the interior. If all the nucleons were lying in the interior, then the volume energy term is given by EV is equal to A1A. So as A increases, it is more difficult to remove an electron from the nucleus, or more difficult to remove a nucleus from the a nucleon from the nucleus, means the binding energy increases. But that is not the actual case. Some nucleons will be there on the surface of the nucleus. Now, the number of nucleons on the surface depends on the surface area of the nucleus. Now, if R is the radius of the nucleus, then A is, that is, surface area is equal to this A. You should take it as surface area. Surface area is equal to 4 pi R square, or it is 4 pi R is equal to, we have learned earlier, R0 a raised to 1 by 3 the whole square. That is 4 pi R0 square a raised to 2 by 3. So the surface nucleons can easily be removed from the nucleus. Okay, much easily than the interior nucleons. So the surface effect reduces the binding energy. So here I can give 4 pi r0 all are constants. So the surface energy is proportional to the surface area, or surface energy ES is equal to, all these I take it as a constant, minus B, and it is proportional to a raised to 2 by 3. Why is it given a minus sign? Because if the number of atoms on the surface increases, then it those nucleons can be easily removed from the surface. So what is binding energy? The energy required to remove the nucleons from the surface of a, from the nucleus. It is the energy required to disintegrate the nucleus. So if more nucleons are present on the surface, we can very easily remove those nucleons. So the surface energy term reduces the binding energy. That is why it is given with a negative sign. So it is highly significant. The surface energy term is highly significant for light nuclei, where most of the nucleons lie on the surface. There are not much interior nucleons. So that term is highly important or significant for the light nuclei. Now, the third term in our binding energy equation is Coulomb energy term. Here, the electric repulsion between a pair of protons is considered, and the repulsion between the protons also contributes to its decreasing binding energy. So, if there is more repulsion, you can very easily remove the nucleons from the nucleus, or the binding energy becomes small, or binding energy gets reduced. Now, let us calculate what is the equation for the Coulomb energy term. So, Coulomb energy is of the nucleus is the work done to bring Z protons from infinity into a volume having the size of the nucleus. So the potential energy of a pair of new protons are apart is given by potential energy is V is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R, or 1 by 4 pi epsilon 0 E square by R. Now, this is the energy between, potential energy between a single pair of protons. Now, if Z is the total number of protons in the nucleus, then how many pairs of protons will be there? There will be Z into Z minus 1 by 2. We know that N into N minus 1 by 2 is the number of pairs possible in a total quantity, in if there are N number of particles. Similarly, if there are Z number of protons, then the number of pairs possible there is Z into Z minus 1 by 2. So the total Coulomb energy is Z into Z minus 1 by 2 into V, or it is Z into Z minus 1 by 2 E square by 2 into E square by, I substitute this value for V here. So it is actually, this R is again our R0 a raised to 1 by 3. So all these terms are constant, which 2 E square, 4 pi epsilon 0 R0. So I replace all of them with A3. So it is EC is equal to minus A3 Z into Z minus 1 by A raised to 1 by 3. Why the minus sign? As the number of protons increases inside the nucleus, the Coulomb repulsion will increase, and the Coulomb energy will thus decrease the binding energy. That means binding energy is the energy required to hold the nucleons together, or the energy required to disintegrate the nucleons together. So what happens is the binding energy gets reduced because of the repulsion between the protons, and it reduces the nuclear stability. So these are the first explanations for the first three terms in our binding energy equation proposed by Weizsäcker. That is EB is equal to plus A1A. That is, as the number of nucleons in the interior increases, the volume energy term increases, whereas as the number of nucleons on the surface increases, the surface energy leads to a decrease in the causes a decrease, or it reduces the binding energy, and the Coulomb repulsion or the Coulomb energy term again contributes to a reduction in the binding energy term. Okay, firstly, only these three terms were suggested. But when we calculated the binding energy using these three terms, it did not match with our binding energy per nucleon curve that we learned in the last class. We had learned the curve for the binding energy per nucleon versus mass number. That these values, when using these values, when binding energy was calculated, it did not match with this curve. So, a few correction terms, two correction terms were also introduced. One is the asymmetric energy term, and the other asymmetry energy term, and the pairing energy term. So those two terms we'll discuss in our next class. So I hope all the things discussed in this session about the liquid drop model is clear to all of you. If you have any doubts, please do contact.